So my name is Marco Cerezo. I'm from Los Alamos National Laboratory, and I'm going to be talking about some of the recent results that we have on what we're calling geometric quantum machine learning. So, the main idea of quantum machine learning, I'm definitely not going to get into details here because I think that we all know quantum machine learning and why it is important. But just very briefly, we want to combine this idea of machine learning and applying the learning methodology to solve tasks of interest. And with quantum computing, what we're trying to do is merge ideas from both fields to obtain what we call quantum machine learning, with the hope being that if we can harness the exponentially large Hilbert space, maybe we can solve some problems much faster than classical computers. So for now, let's just consider it a supervised quantum machine learning problem, although the things that I'm going to be talking about are going to be more widely applicable. So we're going to have some data set, and we're going to assume that the data set contains n-qubit quantum states that are of interest. Those can encode classical information. You take your classical data, you embed it into a quantum state, or they might just be quantum mechanical in nature. Say they're ground states of some model, and you want to detect which phase they belong to, right? And what we're trying to do is that we're going to be trying to train a model, perfect, that is going to map from the data space to the label space. And just as the speaker in the previous talk was saying, one of the biggest things that makes or breaks the success of the quantum machine learning are the inductive biases, or the choices that we make whenever we're building the model. This can include the choice of the ansatz, the choice of the optimizer, which cost function we're using. And it is extremely important to be aware that whenever you're working with a quantum machine learning model, or with machine learning in general, there are assumptions that you're baking into your model. And those are going to be crucial to determining the success. So for us, what we're trying to do is we're trying to take the data, and we want to take the data and analyze it to try to see if there's information about the problem that we can put inside of our models. And as I was saying, why do we want to do this? Because we know that if you don't embed information of your problem into your model, you're very likely to fail. For instance, you might have barren plateaus, you might have poor generalization. And why is this? Because there is no free lunch. So that means that there is not one model to rule them all. We cannot have one model that is all-purpose, that you can use it for every single problem, and it's always going to work. So the more information we put into our models, the more we can expect that it is going to work. And let's now take a step backwards, think about classical machine learning, and talk about symmetries. And this is a very novel approach that people in the literature have taken. So let me just give you a picture of a cat, and let me just take this cat, move it around in the frame, rotate it a little bit. It's very obvious that a picture of a cat is still a picture of a cat, even if I roto-translate the image of the cat, right? So this means that the label cat is invariant under the roto-translation group. And what we can try to do whenever we're working with quantum machine learning is that if I have a model that is agnostic to this fact right here, I'm still going to have to try to train it so that it learns that the picture of a roto-translated cat is still a cat. One way to do this is via data augmentation, which means that I'm just going to give my model more data. I'm going to throw in more pictures of the cat that has been roto-translated all over the place. But the problem of this, it is very parameter efficient because my model needs to have a larger capacity to learn the roto-translations. And it is more also data inefficient. I'm going to have to provide my model with more data. And even if we succeed in training, there is no guarantee that the model will generalize well whenever presented with other roto-translated data. So the key assumption here, or what we're trying to aim for, is that we want to have models that by design are going to be invariant under the roto-translation group, right? That way we don't have to teach it. It's just I give it a picture of a cat. I give it the same picture of the cat that has been roto-translated or acted upon by an element of the roto-translation group, and it's going to give me the same answer, right? So this is the ultimate goal. So people in classical machine learning have been thinking about this for the past 7 or 8 years. And I really recommend this. I would say it's not a paper. It's essentially a book, which is very beautiful. And it's led to the development of the field of geometric deep learning. And the main idea is that they've recognized that all data has symmetries, and that those symmetries are important. And this idea of the roto-translation can be generalized to more groups, and it has applications to many domains. And what's really nice is that in classical machine learning, they've showed that all the models that are very successful, like CNNs, is because they embed symmetries of the model. Like convolutional neural networks, they're invariant under the translation group by design. So they've come to recognize that symmetries that were already in models have been very important. So now let's just, from now on, design models that encode those symmetries. And why is this important? Because it reduces the expressibility of the model. Now, the target function that I'm seeking, this one that maps from data to labels, if I don't put geometric priors into my data, I'm going to have to search in a much wider space. But if I constrain the expressibility of my model appropriately, then my search space is going to become easier. And it has been shown that by embedding symmetries into your model, you're going to have easier training and improved generalization. And also there is this GitHub right here that has a collection of a lot of papers from the classical machine learning literature. Again, highly recommended because there's a lot of really nice work done by the community. So what do we want to do? We want to take ideas from geometric deep learning and we want to import them into quantum machine learning. And the main idea is that we want to build quantum learning models that encode by design the symmetries of the problem at hand. And one of the things here is that whenever you talk about symmetries, you need to talk their language. And their language requires, fairly advanced, not technically, not too advanced, but at least a little bit, of knowledge of group representation theory, which is the language of how group acts, and it describes their action on vector spaces. So we recently put out a tutorial because a lot of us were learning representation theory because, you may know a little bit about it, but you want to learn more. So we put out this tutorial that is by quantum machine learning practitioners for quantum machine learning practitioners. So if you want to learn a little bit more, I would put it here. But just to understand, if I give your group the SO3 group, for instance, this is an abstract object. If I want to see how it acts, I need to define a vector space. For instance, I'm going to define the three-dimensional real-valued space. And then the representation of the elements of SO3 are just going to be like 3 times 3 matrices. And representation theory does this connection between these two things. So, OK, let's go back to this idea of geometric quantum machine learning. And for the remainder of the talk, let's just consider some notation. So I'm going to consider the case just like the previous talk, where I take quantum states, and I send them through a parametrized quantum circuit, which I'm just going to consider to be a parametrized unitary channel, right? And at the end, I'm going to make a measurement. So, via cyclical properties of the trace, I can always apply the unitary to my measurement and think that the model is just take your state and measure with a parametrized measurement, right? So how do we find models that by design are invariant under a group? The first thing that I need to do is recognize what is the symmetry group of my data. Once I have done that, for instance, a very simple statement that I'm going to make here is that if I give you a group G, then this group is going to be G invariant, or its predictions are going to be invariant on the other shown of the group, if the measurement operator belongs to the commutant of the group. What does this mean? That all the elements of the commutant are all the operators that commute with the representation of all the elements in the group. We can see very simply here, if I act with an element of my group on my state, let's just assume that it's a unitary representation because my group is compact and well-behaved. Use cyclical property of the trace, get the R right here, commute it through with the O. These two cancel because this is a unitary. And your model prediction is the same for your data, than with your data acted upon by an element of your group. So to give a concrete example, let's give you the task of, I'm going to give you single qubit states. Half of them are going to be pure, half of them are going to be mixed, and you're going to want to classify them, right? It's very obvious that this is a very well-defined supervised machine learning task. We identify the symmetry, which is all the rotations that I can apply to my data. They change the symmetry. Very crucially, they don't change the label because it's just a unitary, but very crucially, they change the state. I take a state, rotate it, I get a completely different state, so my data is not invariant, but my label should be. A pure state, when applied by a unitary, still a pure state. So now we just need to look at the commutant of the group, right? So let's consider the case where my model just takes a single copy of my state. I need to look at what is the representation of my group. And here, because this is an irreducible group, the only thing in the commutant is the identity, because there is nothing that commutes with every other unitary except the identity. So what this tells me is that I can only do the trace of row identity, which is 1 for every state in the data set. I cannot classify my data, right? And this just came by looking at what are the elements in the commutant. So what happens if I now give it multiple copies, for instance, 2? Now the representation of my group is U tensor U. And you can very easily check that these two things commute with U tensor U. I have U tensor U, I swap them, I still get U tensor U. So they do indeed commute. So now I just need to measure something in the commutant, and we can verify that if I just choose the swap, trace of row tensor 2 swap is just a trace of row squared, which is the purity. So now my model can classify. And we solve this problem just by representation theoretical approaches, right? This is very nice, this is very pretty. But the problem is that in practice, characterizing the commutant can be very hard. The commutant can be very large, And just handpicking the solutions like we previously did might be very difficult. So this is why we introduce, or well, we're not introducing, while we're going to use this concept of equivariance rather than invariance, which is that we need to find a way to systematically explore this commutant, right? So let's go back to the model. Now let's just assume that my model is composed of multiple layers in my parameterized quantum circuit. Each one of them is just going to be the exponential of some Hermitian operator. And what we're going to try to find now is, instead of looking at the invariant measurement operators, we're going to look at equivariant maps, or covariant from the literature of quantum information, which is just the maps that commute with the action of the representation of the group. And now that we do this, it's very simple to verify that if I have an equivariant circuit plus an invariant or an equivariant measurement operator, my model is still going to be able to satisfy the conditions that its predictions are going to be the same for data and for data acted upon by the group. So where do we go from here, right? This is a general statement, so how do we go from here? The first thing that we've done is we've proposed a theory for equivariant quantum neural networks, where the idea is just create a pipeline where you start with data, you identify the symmetry, and you want to build those equivariant neural networks, because just looking at this equation is not obvious how to choose this unitary, which can be identified as choosing this generator, right? But there's ways of doing this. So we identify different methods to constructing equivariant layers. Those are also valid for equivariant channels, so not necessarily equivariant. And there's different methods. They both have uses and weakness on different problems. And the other thing that we do is that we characterize different types of equivariant quantum neural networks that you might be able to see, like embedding, lifting, standard, pooling, projection. These are just names that I'm throwing, but the whole point is that we're trying to characterize the different action of equivariant quantum neural networks. And we also identify their action as being generalized Fourier actions. I'm by no means going to get into that because I would have to get into representation theory, but this is just to say that we're trying to understand what it actually means to have equivariance in a practical scenario. So, the next thing is, let's see this in practice. Let's now look at concrete examples where equivariant quantum neural networks are going to be useful and they're going to provide some advantage over non-equivariant ones. So let's consider problems where my group is just the symmetric group Sn, and now I need to define a representation. I'm going to define the qubit defining representation. That is just the one that swaps qubits, right? So why do we care about this? Because these examples where this is the relevant symmetry group appear a lot of time in the literature. Learning over sets of elements, for example, or modeling relations between pairs, or essentially anything that is defined on a graph or on a grid, such as condensed matter systems. Because if I give you a graph and you want to put it into qubits, the graph just has nodes. But saying this node is qubit 1, this node is qubit 2, the answer of your model should be independent if I had said this is qubit 2 and this is qubit 1, right? So every graph problem should have some Sn equivariance or invariance embedded into it. Molecular systems, evaluating genuine multi-part entanglement, or working with distributed quantum systems are more examples. So now, without caring too much about how we got here, you can look at this circuit, just apply rotations around the x-axis with the same parameter, rotations around the y-axis with the same parameter, and interactions that are ZZ couplings that are entangling, all with the same parameters. It's very easy to see that each one of those layers commutes with the action of the permutation group, because if I permute qubit 1 with qubit 2, I get exactly the same unitary. So this unitary is very interesting because it can be shown to be universal. So any unitary that is permutationally equivariant can be found by having enough layers of this and choosing appropriate parameters. So it's very simple to find an Sn equivariant ansatz. And what do we get from here? Just from the previous talk, we just heard that there's 3 things that we care for. We care about there not being barren plateaus. We care about there not being local minima where I can get stuck. And we care about good generalization. Well, it turns out that for this, we can get all 3. We can get the holy grail of properties, because this ansatz will not have barren plateaus. This ansatz can be efficiently overparameterized with a polynomial number of parameters. That means no fake local traps, no fake local minima. And you can guarantee exponentially fast conversion to solutions. And it can generalize well from few training points. So these are all the nice properties that we can derive for this ansatz. We can also consider other examples. Like now, let's consider the case where my symmetry group is SU2. Its representation is just the tensor representation. So just take any unitary and multiply it by itself. And it's very clear that this is going to be a symmetry that appears in condensed matter systems, for instance. So here we propose a way to build quantum convolutional neural networks with the symmetry embedded into it. And what we're going to have is 2-qubit gates that are going to be unitary, then channels, then 2-qubit gate, then channels. And the symmetry has to survive all the way through this circuit. So if I apply the same unitary to all the qubits at the beginning, it has to commute through and just appear as a unitary here. We have some theory about how to choose all those channels here. But now let's consider a more concrete example. Let's say that I give you my system is the bond alternating XXZ Heisenberg model. This is the phase diagram that it has. This is just a schematic of the interactions taken from this paper by Robert Huang. And this has two phases, a trivial phase and a topological phase. I'm just going to stand at delta equals 1 with a transition when J prime equals J, And this symmetry this problem has SU2 symmetry. I want to classify this. So first, if I have a problem agnostic model, that means just a hardware efficient ansatz where there is no symmetries embedded into the model. And let's say that I only give it 2 training points, one that is standing here and one that is standing here. And I want to train the model to do classification. It's going to be very bad. This is about 0.6 classification accuracy. Just throw a coin, you might do just as well. But if now I use the symmetry preserving model, we get something that looks like this with just 2 training points. It's very obvious that if I take a probability agnostic model and I give it a bunch of data, it's going to do well. So this is just an artifact that I'm just considering the smallest number of training points that I could ever give to each one of the models. So there are some practical advantages in terms of there's going to be less data requirements, less parameters that I need to consider, and better performance here. So embedding symmetries into your model should be something that we should be using. If we have information, why are we not using it? This is particularly true when working with classical data, because a lot of times we take classical data, we put it into quantum state, all the symmetry information is gone. The way in which we take classical data and we put it into quantum states should respect the symmetries of the data. It might change the representation of the group, sure, but we need to try to keep those symmetry information relevant. So just to close up, geometric quantum machine learning provides a framework to encode symmetries into our model. It can help mitigate critical issues and give us, the trifecta of all the nice properties that we want for theoretical guarantees. And the thing is that there's been 6 years of work in the community of classical machine learning. For quantum machine learning, it's a handful of papers. Everything is a low-hanging fruit. We like low-hanging fruit, so in this field, everything is a low-hanging fruit. And a lot of work is needed here. So, we're just encouraging people that if they're interested in this, get in touch with us, because there's a lot of work that needs to be done. And the mandatory disclaimer, this is not going to be a tool that is going to solve all of your problems. If you have a very small symmetry group, you can expect a very small improvement. So don't think that just because I put symmetries into my model, everything is going to be solved. Final thing, I just want to give a big shout out to my co-authors, a lot of summer school students from last year's summer school at LANL, collaborators from Google and at Los Alamos. And just to say that Los Alamos has currently open postdoc positions, and our applications for the quantum computing summer school are open. This was supposed to be updated with a link here, which I guess it didn't got updated. But if not, you can just send me an email and I can send the information. And thank you very much for your attention.
All right, we have time for a quick one. Okay. Sir.
Hi. So just to talk about an example, if I have a sequence of images of cats and dogs, and I would like to train them. So typically the way it is done in quantum machine learning is you encode them into some rotation gates, and then you choose some trainable layer, and then you train that, and then you classify that, right? So in that example, how would we use the technique that you described, this symmetry aware, or like embedding the geometrical symmetry of the inherent problem, and then utilizing that for better convergence, better trainability, et cetera? Thank you.
That is a fantastic question, and I would say it's a low-hanging fruit for you right there, because I don't know. Like, mostly we've worked with quantum data because the symmetry is already in your data. Whenever you work with classical data and how to put that from classical to quantum, how do you get elements from the Roger translator group acting on a grid of pixels to quantum states? I don't know. We probably need to define new and better embedding mechanisms to get classical into quantum data, and then also build a model that is going to respect those symmetries throughout the computation. So yeah, that's a great question. I don't know the answer to. So if you're interested, I would encourage you to work on that.
This is about the encoding of the problem.
Yes. Oh, everything should have the symmetry embedded into it. The encoding part, so that you get the symmetry from classical data to quantum data, and then the ansatz, the parameterized quantum circuit, so that your symmetry gets respected throughout the computation. So the whole pipeline should be symmetry aware.